General relativity, step by step. Last time I derived this equation of state here for an ideal fluid characterized by its density ρ0 and pressure P0 in its own rest frame. And I want to spend a bit of time talking about this equation because there's more going on here than you might think. I'm going to follow Kip Thorne's advice again and consider one idealization after another. And of course, a dead easy one to do is to consider the case of a pressureless fluid. So P0 equals 0, we're considering a dust. If you can, the equivalent in room temperature or kind of terrestrial environments is a gas at absolute zero. Because if the temperature is non-zero, then in your little box here, the molecules are bouncing around and they're exerting pressure. They're exerting pressure on their surroundings. But I'm not going to consider that. I'm just going to consider them sitting there at rest. Dust. In that case, of course, this equation simplifies a little bit. We've got di by dt of a cubed ρ0 equals 0. And your first observation is to say, duh, well, of course it is. If I've got a little volume, A by A, and its density ρ0, and it expands a little bit. Get rid of that. Just a minute. And it expands a little bit, so it's A by A by A, and it's ρ0 dash. Then, of course, by conservation of mass, that says that ρ0 A cubed on the left-hand side equals ρ0 dash A dash cubed, I guess, which is what I've got written down here. However, it's not as obvious that this is the case. If I take two black holes here, and they're by some means stationary, and then I pull them apart somehow, I might put an electric charge on it and kind of drag this one away and drag that one away there, then I've done work on that system. I'm doing work. And if I'm doing work, then I'm incrementing the energy, which increments the mass. So we've got this situation where I've got these black holes and I'm moving them apart and I'm increasing their mass, the collective mass, simply because I'm doing work on them, and E equals mc squared. E equals mc squared. And it's not clear that that effect, well, it is clear that that effect well, there's no net effect of that going on here, because when you increase your little control volume here, which has got galaxies and stuff in it, you're pulling them further apart in much the same way that you're pulling these black holes apart. Well, I say you're pulling them, they are moving further apart, because that is what space-time is doing. And it's not clear that that effect isn't important. There's also a gravitational interaction between what's inside here and what's outside here, and so there's mass outside your little control volume which is attracting the galaxies inside this little control volume, and that's going to have an effect on the energetics, which is going to have an effect on the mass. So there's all these effects going on, all of which might cause you to doubt that di by dt of ρ0 A cubed equals 0. Oops. But it's true. So it's a non-trivial observation. I'm going to put the pressure term back in. Where are we here? I'm going to put this pressure term back in and see what happens. So we've got, I'm going to pinch in, di by dt of A cubed ρ0 plus P0 di by dt of A cubed equals 0. And of course what's going on here is that if we have some substance in a little control volume and it gets a little bit bigger, is that bigger? Yeah, there we go. The perspective isn't very good on this. A dash, A dash, A dash. Then if it's expanded in an environment of pressure P or P0, then it's done work on it. And so you normally think about this in terms of the first law of thermodynamics. And you usually see it written in this form: du equals minus P delta V. You usually integrate this guy up here. So again, it looks like we've got a completely boring pedestrian sophomore level physics kind of addition to our conservation of mass, but we haven't. Let me remind you what the components of the stress energy tensor are. We've been considering the stress energy tensor with one upstairs and one downstairs index, and the time, it's diagonal, the time component is minus rho 0 minus cosmological constant over 8 pi g. This is all for an ideal gas. Sorry, a perfect gas. And the components, the spatial components, theta, and what's the other one, phi, were all the same by construction, being p0 minus over 8 pi g. And what else did we have? We also had the stress energy scalar T was minus rho 0 minus p0 minus 4 cosmological constants upon, not 4, 8 pi g. So we've got these different components here. I just want to make the observation that in this one here, the cosmological constant and the density are of the same sign. But in this one here, they're of opposite sign. So the cosmological constant is kind of like some sort of thing with, if you imagine the cosmological constant is positive for a moment, then it's got sort of positive density but kind of negative pressure here. Sorry, there's a 3 missing from there, 3p0. And who knows what's happening here. So the cosmological constant is like a sort of positive density but negative pressure source term. And given that, it's entirely possible that the cosmological constant, it would take work to expand space. It's quite conceivable that the cosmological constant would mean that it was harder, or perhaps easier, to expand space than you might think. But that's not the case. This law here shows you, well, there's no cosmological constant in it. The cosmological constant disappeared. It cancelled out of our equations for quite subtle reasons, but it did cancel out. So there's no cosmological constant in this, no lambda in this, which is surprising. All I want to say is that in general relativity, apparently simple-looking equations actually can contain quite powerful insight and powerful truths. And in this case, this particular equation took us an enormous amount of time to derive. It was very complicated. We had Christoffel symbols, and we had a whole bunch of cancellation. We had a whole bunch of differential equations. It was decidedly non-trivial to evaluate. There's just some... Oh, has this one gone on? This one's gone on for 8 minutes. I've got a little bit of time. Yeah, if I go back to the field equations, I mean, there's different ways of expressing this, but let's just go with the standard way. We've got the Ricci tensor mu nu minus a half g mu nu times the curvature scalar, plus the cosmological constant times g mu nu equals what's the constant? It's 8 pi g t mu nu. Those well, it's one form of the Einstein field equations. There's others. Now, effectively what I've got here, this is curvature. Well, I guess geometry rather than just curvature. Geometry. And this here is sources. Because we've got density and matter doing things and affecting the curvature of space. Now, what I did in order to solve it was take this guy here and put him on there. So, effectively I was destroying him and putting that there as if this is a source. Now, there's nothing wrong with that mathematically. Of course, I can do what I like mathematically, but philosophically what I'm doing is I'm treating the cosmological constant as though it was a source. And that leads to a whole bunch of equations like this for the different components of the stress energy tensor that incorporate this peculiar source called the cosmological constant. But it's not clear to me that that's an appropriate or correct way of thinking about it. It's plausible, well, it's correct that the cosmological term is a feature of space-time itself, which you have to account for on the right-hand side, sorry, the left-hand side of your equations, rather than just being another source, which can just be added and subtracted to the effective matter in your universe. So I just want to make that observation that I'm casually moving terms from the left to the right-hand side, which is no problem at all. The problem is, do we consider that to be a legitimate physical process? Is it legitimate to consider the cosmological constant as a source? And it's not clear to me that it is. Stop.